Is this working? Great. Okay.
Yes.
Um, Thank you so much to the organizers, to everyone who was putting this together and running it online, and to Elhanan and Eric for the invitation. I'm very excited to talk. I've learned a great deal from the talk so far. I'm going to talk about a project about supply network formation and fragility, and disruptions to production during the pandemic. And this is joint work with Matt Elliott at Cambridge and Matt Leduc at the Paris School of Economics. So I'm going to start by telling you the shape of the model I'm going to be interested in. Then I'll speak about motivation for an unusually long time, but I wanted to get into the same space of thinking about models before we talk about the world. So I'm going to be interested in processes of complex production. And by complex, I mean that there are many steps to this production, and each of these steps involves several essential inputs. So, for example, to make an airplane, these are chosen partly for alphabetical reasons. To make an airplane, you need to source brakes and computers. And these are complex things that don't grow on trees, but they're made of other produced inputs. And one feature that's increasingly important in modern industrialized economies, has been for a long time, is that a lot of these inputs are specifically made for the thing that they're put in. They're not generic. So that means that if you're an airplane manufacturer, you're not just sensitive to the supply of brakes in the economy, but the particular kind of brakes that go on your airplane, that you need to source to produce. And so firms understanding that disruptions in individual supply relationships can leave them in trouble, multi-source. And the picture I want you to think of throughout the talk is this: that we have a little airplane manufacturer, and this airplane, as I mentioned, needs at least brakes and computers. And it has two brake manufacturers that it has the potential to source from. These could be actual supply lines that are running, or it could be a sort of agreement. But in any case, these are sort of pipes along which brakes could be delivered to our airplane manufacturer. And then the key thing is that brake manufacturers all use other things themselves, for example, disks and smaller computers. But this picture can proceed for many steps. And so I've filled out the rest of the tree in some kind of way. Okay, and I'm going to be interested in this kind of, it's a network, in some ways similar to the network of transmissions that was implicit in Glenn's talk, but of course different in important ways, and I sort of motivated by completely different economic forces. And to give you a preview of what I'm going to do in this talk is we're going to be just trying to understand how robust is such a supply network to shocks, especially aggregate shocks. And that's, of course, where the pandemic comes in. So as I'll talk about in detail in a minute, the pandemic has led to a systematic disruption in sort of the tissue of the production economy. And we're interested in understanding what that's going to mean for productivity, among other things. So there's an exogenous version of this question, which is just an applied probability problem. You specify the network, the distribution of shocks, and ask what fraction of firms can produce. And this question is already somewhat interesting. And I'm going to show you a phenomenon about it that you may recognize from some other things, but that's going to be important for us. And then the version that's really distinctive to us is that we're going to take, or that I'm more excited about, is that we then, of course, think about these decisions. How hard do you work to source the supplies you need to produce? A part of an economic equilibrium. And we're going to try to understand how robust are equilibrium supply networks. And the main finding is going to be that there is what we call a fragile regime where aggregate output is very sensitive to small systemic shocks to relationships. Another way of saying this, maybe more informally, and of course I'll give you theorems eventually, but an informal way of saying this is that it can happen that many supply chains simultaneously freeze up and stop doing what they're supposed to be doing. And I'm going to argue that this is not just a possibility, but being on sort of the freezing boundary is a natural endogenous outcome that happens because of the way supply chains work, because of the incentives that firms have. So that's the very big picture. That in a sense is as much as I can fit on one slide of what I'm doing and where we're trying to go. But having laid out a sort of model in words, I want to talk about why we really want to suggest some of these forces as being interesting for thinking about COVID. So here's a story that ran on the front page of the New York Times on June 1st, very recently. And this article, like many of you probably have read it, it talks a lot about manufacturing practice, which is now not exactly, the state of the art, but certainly a very influential management practice called just-in-time supply, which is where it was developed by Japanese firms by the 80s, and they very extensively sort of developed these deep supply chains where they didn't keep a lot of inventories. And the article has this narrative that the inventories have been cut increasingly, so firms are running very lean, and then they're unprepared for whatever trouble inevitably emerges. That is, when we go back to our little picture up here, if you're not keeping a lot of breaks that you can use, on a rainy day, then you really are reliant on being able to get breaks when you need them. And this article has good stories about this actually happening. So they talk to a chemical company owner who is, first of all, reports that he has tenfold more than usual delinquencies that he's experiencing, that he can't deliver because of supply problems. And so usually he only has 1% late. Now he has 10%. And an example of why that happens is he can't get a certain resin that he needs to put in his construction materials, that he can't make the resin that's his product because the supplier of that was lacking a Chinese input from a particular plant in China. So this is sort of live evidence, and it's easy to find this in the sort of trade press that you can find disruptions that are caused by 2 and 3 steps away. Another example that's given here is even something as simple as metal cans for putting paint in. If you can't, they need to be compatible with your machines, and the absence of this simple part makes it impossible for another manufacturer to produce its paint. So there are multiple essential inputs at each step, and you really can't do without all of them. So there's a lot of quotes in the article about cascades and contagion. And again, a narrative, the article keeps repeating, oh, they should be running with more inventories. But when they interview a supply chain expert, they say that once your production gets very complex with many product lines, the way current firms work, inventory isn't a magic bullet, because just the logistics problem of keeping enough inventory and managing it across a lot of these necessary inputs is just not necessarily going to have, it's not going to be that effective. And so just in time is sort of increasingly just a necessity of the way production works. But I really want to highlight a more normative aspect of this New York Times thing. They say these firms were all running too lean, and maybe they'll learn a lesson now and have more robustness, but maybe they'll still be greedy and pursue cost savings. And so to an economist, this raises obvious questions like, is it really, do we think firms need to be myopic or misoptimizing for these problems to happen? What's the nature of the externalities? Is it possible that aggregate outcomes are bad? Not because perhaps of some kind of naive mistake, but because there's something intrinsic to the system that pushes it toward bad points. So those are the kind of questions that motivate us. And those were anecdotes. I'll just show you two or three very quick graphs. This is from June 17th, so very recent, excellent little article by the Council of Economic Advisors. They have census data that shows that indeed inventories have experienced basically unprecedented severe drop. So suddenly there's all these shortages, what we're going to interpret as a sort of freezing event. These are happening predominantly in industries that put a lot of things together, like manufacturing and construction, consistent with the picture I've sketched for you. Of course, we don't know, this is saying that in the last week, more than half of firms surveyed reported delays. Is this normal? No. Okay, this graph shows that these shortage reports are indeed very unusually high relative to typical for these industries. And the fact that their own inventories are low, of course, means that if they have any hope of filling their next orders, they need their suppliers to be available just in time. And so there's a kind of feedback loop to everybody needing their suppliers to be active now. So we're going to be modeling all this and trying to understand what are the externalities. Do we expect the outcome to be inefficient? Why? Sergio, I saw you briefly. You're good. Okay. And by the way, I'm like Glenn. I welcome questions. Love to talk. I'm watching the chat too. So please prevent me from sort of. I'll show you one more. So I know this is Hebrew use standards. I'm not gonna. Pretty soon we have to start doing model stuff. But I want to just say one more thing about a key ingredient in the model, which is from a different article. And the question I want to ask now is sort of what is causing, what is the shock that's causing this problem? Now, of course, you could say COVID. COVID is somehow causing this problem, but the supply network is not a person. It didn't get sick. So what exactly is happening? And just for a little color on that, there's another article. I probably should have used at least 2 newspapers, but the New York Times has really developed a beat around this. And going a little further back to March 6th, they talk about exactly part of what the shock has done, not in its consequences, but more directly. So their overall take is that the virus has, quote, thrown off the choreography of moving cargo from one continent to another. So changes in shipping inconvenience and cost is really some of the most striking direct, getting closer to the cause, right? So you have threefold increases in freight container rates, 90 days to ship something that usually you can get, that these people don't have delays for. And this executive at Maersk says that all the links in the supply chain are stretched. So every step in connecting these relationships between firms. And from the article, I'll just give you a very quick sense of what kind of stuff happens. So one kind of thing that makes each relationship work less well is that there's a mismatch between containers that you put stuff in and the ships that carry the containers. So there was some emergency shipping of ventilators. Containers ended up in places that are not, in the global south, in Africa, and random places in India. And then the ships are too busy to go pick them back up. So now people have to add a 1,000-mile trip from Kolkata to Mumbai just to find a port with containers there. Then the ports themselves are congested because the workers are quarantined, there's limited staffing, workers don't come to work because they have to take care of their kids. And finally, just logistics management seems less efficient. So you have ships taking empty containers back to China because they're so demanded in China, rather than doing the usual thing where they wait to take US stuff back to China. And so you're just getting less out of the whole shipping network. So it's sort of plausible that it's affecting, the whole system. The argument I want to make is that, this does seem like a global phenomenon in response to a global shock. And we see many seemingly unrelated sort of different supply networks simultaneously being affected by this. But I don't want to, if we sort of have a biology metaphor, I don't want to think of this as like a blood clot. One way you can think of getting really sick is you have a blood clot, it starts in one place and then it messes everything up. And this is arguably more like just a whole body inflammation. You can't find like a single domino that caused all of this except for the virus. The virus sort of created all these random problems in all of these different links throughout. And so we're going to be modeling that. Of course, there are papers in macro and networks that study the propagation of granular shocks, like domino effects. We're not going to be, we're about different forces. Now, current network macro is very interested in nonlinearity. So Bakai and Fari have an amazing line of papers. Fari, of course, is tragically no longer with us, but any of their papers is an amazing bibliography on the more macro way of doing these things. Going back to Chad Jones in 2011, these are all citations from our paper. But these macroeconomists, what they like to do is differentiate things at the end of the day. They like taking derivatives and characterizing the impact of shocks as like, a big first order effect, or maybe if the first order effect doesn't explain it, something about the curvature. And we're going to be taking an approach that's based on network theory, and that's going to really focus on the details of freezes. So we're going to consider a fairly standard kind of reduced form model of a supply network, but we're going to let links fail, just disappear, not work. And this is called a percolation model. It's actually, you can write a disease transmission model as a percolation model. So you have a network of links that are supposed to be working, but then some of them get knocked out and they're not working. I think Glenn's papers do cite some of the more, sometimes this graph theory perspective kind of pops out in the background of some of these SIR models. In an economic context, Matt Elliott and Matt Jackson and I have a paper where we study financial contagions using kind of classic percolation tools. But it turns out that when we have a complex production process, which has the structure that I've described to you, failing, the consequences of random failures are much less understood. There's some recent applied math that suggests that these contagions have kind of percolation features that are different and interesting relative to sort of, what many people know from basic random graphs. And so we just want to do the simplest percolation exercise in a complex production economy and understand the implications for endogenous investment, and then think about the externalities and inefficiencies. So that's where we're going. And now I'll be telling you about, I'll starting on the next slide, I'll tell you the math. So this is a great time for questions, complaints.
Ben?
Yeah.
I'd just like to come back to your discussion of shipping and the one lesson you could draw from stories like this is that manufacturers who are using many parts should be concentrating more on domestic suppliers rather than international suppliers. And you sometimes read that in the press that globalization maybe went too far. Do you or your model have anything to say about that?
That's a great question. Yeah, I mean, I think that's a great question. I think I'll defer more than half of it to a slightly later time, but I agree with, the one first thing to say is that certainly during the crisis, there's a very well-loved paper by Barrow and Sauvagnat, which looks at whether firms are good at substituting a supplier that goes down. And it seems that it takes a long time for firms to reconfigure their supply network. So this is a more of a long-run investment thing. And I do think that as we'll see, the externalities are such that there can absolutely be benefits to, the same supply network might not function well when it's susceptible, when it has a sort of relatively high cost shipping tech. If you have one shipping technology that has a higher cost of robustness and another one that has a lower one, call it the domestic one, then it can be that you can sustain production with the domestic one, with the local one, that just would not be possible in equilibrium. So there is a version of and I'll highlight that point when I thank you for that question. Any other questions?
Yeah, if I can follow up on that. In fact, I'm asking about data now, not theory. Okay. Were there similar things observed, say, in tracking or railway, like let's say local US networks?
That's a great question. I
I
don't.
mean,
I
it's a
don't know.
different, it's a different scale because the total time it takes is shorter than shipping. But still, do you observe the same phenomena locally? I mean, locally, I mean in a big country. Yes, not in Israel. Yes, it's
Yeah,
still.
no, that's a great question. So I don't know. The one thing I know is that air freight has gotten extremely expensive because firms are very eager. Some firm, they're willing to pay a lot, but that's still far. So I don't know, and I will find out, and that's all I can do. I do want to say one thing, that for a lot of, as you know, for a lot of this manufacturing, even if for stuff that there's in the normal course of things, it's pretty common for things to cross oceans many times in the course of being made. So just because the production is getting more and more kind of divided. And so I'm not, the question of whether they're purely, almost all complex manufactured goods have had this, surcharge added to them. But I like your question.
Yeah, because that will say if it's really a question of the network, it doesn't matter what the scale of the network is. You should be able to see the same phenomena also when you're talking about locally inside USA networks. Yes, of a different scale, of course, but still.
Yeah. So to me, right. So I mean, I'm agnostic in some sense. If I have a network, it may be that the links that the network that I need these fragile links will only be the overseas ones in a model where domestic shipping is very robust. That would be a different network to study. But I agree with you that I do think my sense is like the one thing that I've read is that, of course, the containers that go on trucks are also coming off the ship. So there's just a general scarcity of them. The logistics of them is disrupted, and so I think that should have an impact on trucking. But I will not speculate further. But I will provoke more questions from Sergio by showing him a model. So
can I also ask a question?
Yeah, absolutely.
Before the model. So you're saying, so the basic problem is I need to produce something. I need this this input, and my supplier can't supply it. So my question is, well, why can't you get another supplier? And so, do you have a sense of, is this a matching problem or a monopoly problem, or like where is the bottleneck of just
good question. So I'm going to allow you to have, I'm going to allow you to have 100 potential suppliers you could call up and ask whether they're available. That's sort of here or there. So in this picture, there's this airplane manufacturer has 2 computer manufacturers that you can call up. And these links represent whether that shipping lane is working correctly now, right? So maybe this isn't 2, maybe this is 6 or 100 potential ones. And we're going to have an endogenous search effort where you basically the probability of those links actually working for you is something that you're going to invest in and choose. So at some level, I do have your basic force in the model. The only thing I don't assume is that there's this truly unlimited continuum of commodity suppliers that if one doesn't work, you can always get another, and that I think is intrinsic to the nature of this production.
Great, thanks.
So really, the math this is a very big slide. I'm just going to fill it up like this is my dream to do a little chalk talk. I'm going to fill this up, try to fill it up like a board. And I just want to tell you one piece of math, which is really okay. There's going to be a little too much notation for my taste. We need it, but all I'm doing on this slide is trying to calculate the probability that A1 is able to produce under a certain distribution of shocks. And so I'm going to tell you exactly how it works, but for reasons so that I can do some kind of macro-ish stuff later, I'm going to put a bunch of these little people in this big continuum supply network. So I don't have just one of these trees. I have uncountably many of these trees, and I can use laws of large numbers. But don't let that distract you. Really, we're at the end of the day trying to understand the behavior of one typical tree. But I'll tell you the notation for the whole thing at once, okay? So we have a finite set of products, which are like A, B, C, all these different types of products. And the nodes are small specialized firms that produce differentiated goods. Small means there's no granular firms in this economy. Everybody is infinitesimal. And so here, the airplane supplier A1, his index is 0.1. So indices are going to be real numbers between 0 and 1. Every type of product has a list of essential inputs, a set of essential inputs, here B and C for this guy. And these are the things you can't go without in making that A. And then we're going to need to keep track of the notion of depth of a variety. So here, if this does indeed end here, right, assume that these things do grow on trees, the depth of A here is 2 because you need 2 steps of specialized sourcing until you stop. And we're making this kind of symmetry assumption that it gets cut off at the same place, which is not essential, but does help with my pictures. In the background, there's going to be a distribution of these depths because I'm going to be interested in, maybe some production can be fairly shallow, but some is going to be deep, and I'm going to have some distribution. And for concreteness, you can think of, maybe a Poisson distribution with some mean. And we'll be interested in making these supply chains somewhat long. Think like 7, 8, 9, 10 is where our results are going to become interesting, which are realistic lengths. So now I'm going to tell you, so this is an example of one such tree, but I'm going to tell you what this supply network looks like, which is a combination of all these trees. So this is a directed graph on uncountably many nodes, all the firms, and there are directed links that are these arrows, who can source from whom. So I'm going to give you for this talk an extremely symmetric case that will be, which I hope will entertain you anyway. And I'll explain, I'm sure you'll ask me, I'll explain why the symmetries I'm using aren't critical to the points I want to make. So here's how I'm going to cook up the network. Each firm is going to need M distinct input types. So here M is 2, it needs breaks in computers. And if it has positive depth, like this guy downstream here, it's going to have some number N, here N is also 2, of potential suppliers, as I discussed with Nikita already, right? So the idea is that this airplane manufacturer will have 2 brake manufacturers in their Rolodex. And these will be drawn. So for understanding a single tree, I don't care who they are as long as they're all different. But just to be totally concrete, I'll say that I draw these people uniformly at random from the industries that are populated by that kind of firm. And if a firm is depth 0, like these guys down here, it doesn't need any specific sourcing. Okay, so it's always going to be functional. Maybe it needs inputs, but it can just buy them. It doesn't need to worry about any of these disruptible links. So now what I'm going to be interested, so look what happened here. So we went from this, the dotted lines are a potential supply network where so I have this one tree of this particular airplane manufacturer, and these are all the potential links involved down to the most upstream layer. I'm going to be interested in studying a subnetwork, which I just transitioned to, where only some of these links are kept. And this is the percolation process. This is where I kill some of the links and make them not work. So more formally, I'm just taking a subgraph of this graph where each supply link is present independently with probability X. So I kill some of the links and I keep some of the links. And the parameter X, for now, just take it as a parameter of the model, is called the relationship strength. Think of it as the probability that the relationship works as intended during a certain time period, a week, a month, whenever this model is sort of whatever time scale you want to think of it. I'm going to just turn down my AC quickly. Any questions? Anything I've been unclear on? Okay, so what I'm going to be interested in is understanding the reliability of the supply network, which again is just the probability that A1 can produce. But let me define it kind of with respect to this continuum of firms. So looking at a given firm, you can kind of inductively decide whether it works or not. So let's do this little example to decide whether A1 can produce. So look at this little B2 firm, right? Unfortunately, B2 needs a G input, and both of its links to G inputs are not working. Those ships are very late, right? And so there's no way that this guy can make his product. And so even though this link would work if it were needed, there's nothing to send down it. And so A1 can't get breaks through this link, and this link isn't working. So through 2 steps of this inductive destruction, we have seen that A1 is dead, right? A1 for this period, with this realization of links, A1 is not going to be producing.
I have a question.
Yeah.
Very quickly.
Totally.
So we're assuming that B1 can produce, but its ships are running late. A scenario similar to that, correct?
That's right.
Okay, that makes sense.
And so we'll call A1 not functional for, maybe A1 will be back next week or next month, but not now, right? Any other questions? So I'm going to focus, for really the star of the show here is going to be a number I call rho, which is it's the reliability of the economy, of the supply network, which is simply the probability that A1 functions. Now, of course, this depends on the depth of A1. Different A1s, depending on how deep their supply networks are going to function with different probabilities. And so really what I'm going to be interested in is the expected, the probability when I average over all depths. And remember, mu is the distribution that tells me how many guys are there of depth 0, 1, 2 in this economy. And so I'm going to look at the fraction of firms that can successfully produce. And in the background, of course,
M and N are fixed throughout.
Exactly, M and N are fixed. Okay, so this thing will essentially be a function, at least in some limit of N and M only. In the background, I'm not bothering you with the macro, basically a little macro model that we worked out, saying, well, if you actually have this network and you make stuff on it the way that the macro guys model it, you get a welfare function. If you have a consumer with love of variety who likes the different varieties, likes to consume many of them, then of course the more firms work, the happier this consumer is going to be. And so we like making her happy, the household, and so we want rho to be higher. So that's why we're interested in rho. It turns out to be 1-to-1 with welfare, if you want to crunch that out.
So just to make sure, M is bad and N is good, because N are substitutes and M are complements. Is that correct?
Exactly. Make it more, yeah. So M as in mom is bad. It makes it harder. Yeah.
Yeah, because you need each one of those M, but for each one you have N different alternatives.
Exactly. And so here's what we're gonna work all this out, but I'm gonna brand the phenomenon that I'm about to show you. I call it a precipice. We say that there's a precipice that can happen in reliability when supply networks are deep. It's possible that reliability and welfare depend on relationship strength in an arbitrarily steep way. Let me just show you a picture. Okay, so here I've taken a particular distribution of depths. Nothing weird going on, just some Poisson distribution if you want, and plotted what reliability looks like as you vary x. Right? And you see that it's kind of very low and then very high. And if I take deep supply networks, which means for example, in this example, I've just let tau go to infinity, I converge to this picture where, let's do it in math, there are positive numbers. There's a positive threshold here, so that below it, you're producing nothing. That is, this typical A1 is not working. Of course, this A1 is going to be deeper than 3. It might be, 7 or 12 layers deep, but it's not going to really be able to produce almost ever. And then when X crosses this critical threshold, it's going to be producing not only a positive amount, but above some critical level, which for this 2 example is something like 0.7. So there's really a stark kind of percolation discontinuity that happens. And so if you're thinking of it as a planner, right, imagine this is kind of centrally planned, and you're just deciding how much to order your managers to sort of monitor the supply lines and hold inventory and all that. This tells us that, there are places where tiny investments have incredible marginal returns. There's sort of almost like a development transition where once your economy gets on the whole robust enough, you can suddenly do you can do something where you could not do anything in this complex kind of production before. Any questions about what I've said?
I'm just wondering about making N, I think, the number of firms of a certain variety endogenous, letting them enter zero profit condition.
Yeah, that's a great. So I haven't. We will make something in. Yeah. So firm endogenous entry. We actually have worked that out, but I think so the number. Yeah, you can do a model. You can do an entry model. I'm gonna claim to you. I'm gonna endogenize something simpler, which is X, right? Let's endogenize X first. But then it is. I agree that you could also then endogenize M2, and that might be. I wouldn't call it, because M is, I think M is a technological number, right? It's the complexity of production. And then how many firms you can access, that's about entry. Do I understand you correctly?
Yeah, I meant the number of not
Yeah.
different varieties, the number of firms in a variety.
Perfect. Yeah. Good.
Yeah.
So I'll say something about that. So let me show you. What I want to do now is I want to tell you why this result, what's going on here.
Just a technical something. When you talk about distribution of depths, you only talk about things that are final products like A, or you also count all the intermediates, like the B's and the C's.
Oh yeah, no, these people all count. But the thing is, it doesn't.
So changing N will have an effect on mu also.
Yeah, yeah.
Although if you only look at the A's, then this will not have an effect. But
that's right. That's okay. Right. Okay, so let me try to tell you. It's not hard to understand what this phenomenon is. So I'll just show it to you, and I can show it to you in pictures. So let me define. This is like the engine under this paper. I'm going to define a function. It's over here on the y-axis. It's called script R, and all script R says is, if I have a firm here and its suppliers operate independently with probability little r, what is the probability that this firm will operate? Okay, this is a little probability problem that you can just work out, on a napkin, and you can define it for any, there's some symmetry implicit in that exercise that all of these guys, for example, are going to have the same r, but you can work out what that probability. Basically how my supplier's reliability, their functioning translates into mine. And so let's do a little, so speaking of this guy, who has all these depth zero suppliers, well, they always work. That's what's great about being depth zero. So if I just evaluate the R function at 1, that's the red curve, I get a number. And of course it's not 1, because it could be just by bad luck, all of these supply links fail. Each of them has a chance of failing for X less than 1. And then we can't produce. So that gives us a number. Now, if I want to figure out what is here, this depth 3 guy, what's going on with him, I'm going to take that number and plug it back into the function R. So I'm going to bounce it off the 45-degree line and plug in that number into the red function again. And that's going to give me the reliability of a depth 2 guy. And I can keep going and do this for any depth. And then to figure out the kind of limit depth I'm interested in, I'm going to go, this is really what we'll be talking about, the largest fixed point of the R function, where R intersects we start at 1, we go down to the largest fixed point. And this picture always looks like this. And here I've zoomed out and I've shown you this picture, we were zoomed in somewhere around here. Zooming out, what we see is that what I've plotted for you is the same curve for different values of X. Okay, you were all interested in varying N and M. That's interesting too, but let's fix N and M and vary X. Okay, you can see you can see now how these curves look. This is the 45-degree line there, and you can see how these curves vary as I change X. Sergio, do you see why the precipice? You see the precipice now? I'm trying to decide if my pictures make any sense. Are you convinced that now there will be a discontinuity?
Yeah. That's yeah.
Yeah. So you were, but I think the answer is yes, right? Oh, did I lose? Can people hear me? I'm worried. I was worried about my connection. Does it seem okay?
You're fine.
Okay.
Sergio was disconnected.
Got
Sergio
it.
was like bouncing.
Oh,
Okay. So yeah, so notice what happens here. This curve, like if x is a half in this example, the curve doesn't touch the 45-degree line. And so actually, if you carry out the procedure that I just said, you're going to go all the way down to 0. And in fact, for x equals a half, a deep supply network won't be producing anything. So a half is below x curve. But at some magic point, at some magic x, this curve, this R curve will just kiss the 45-degree line. And that's where the first positive equilibrium will emerge, and it'll be far away from 0. That's what's going on. Let me show you a contrast. So in this precipice proposition, I assumed M, the number of complementary inputs you need, is greater than 2. Sorry, is at least 2, actually, I should have said. Suppose it's 1, okay? So here I've drawn the same pictures for you, but with M equals 1. So what is this? This is an homage to yesterday's speaker, Michael Kramer. So if you remember Kramer's O-rings paper, right? He studied basically a line of things being assembled. So fixed depth. He studied that you need every step to work in the O-ring theory in order for the thing to work. So you can kind of put that in our model. Of course, if you have long chains, you still need redundancy. Otherwise, just the randomness will get you and make your long chain fail somewhere. But if you do have redundancy, you can study simple production in exactly this. So here, basically, you'll only be custom sourcing one input. Only the brakes are custom here, and maybe only the disks are custom here. Otherwise, so it's like a narrow slice of this tree. And the picture looks very different, right? You'll notice that in this case, there's no precipice. There's a kink. And the reason is that this R curve is not, let's go back here. Notice these curves had this convexity to them. That's what created that emergence of discontinuity. If we have the simple production, the R curve is concave. And so the values are the values of rho are just the points of intersection. These points of intersection gracefully go down to 0, right? So there's a very different form of you might be, you might have been thinking this is some kind of tree. So what kind of percolation fact am I going to use? What kind of giant component is this? It's different from the one you may be familiar with. The one that you see in most simple random graph models is kind of this sort of transition. It's a phase transition, but continuous. And here you see that in our case, because of the difference of the shape, you have a discontinuity. So there's one more thing to explain, which is what is accounting for the difference. And what causes the difference is that these curves are so shallow here near 0, right? That's what makes it impossible for there to be fixed points near 0. They either have to be high or just at 0. So this R curve, which translates my supplier's reliability to mine, is very shallow around here. The reason for that is if you imagine my suppliers are all very unreliable, then my chance of producing anything is a small number squared, right? So it's going to be very unlikely that I produce anything. That's why this curve is basically 0 to a first order approximation here, and why it can't intersect. That may be, so don't worry about that if you're not, that's for the nerds who want to know exactly what's going on. But I hope that's sort of the full intuition of the mechanics of this model. I'll stop here for a second.
I wanted to ask, so if X is indeed reflects the probability that my ship arrives on time, then everything makes sense. But if X is the strength of a relationship in the sense of me, like a supplier, being very committed to bringing the goods to the producer on time, then it should be different. So if my relationship with if B2 and A1 has a weak relationship, then B2 needs to have a stronger relationship with A2.
Good. Okay. So you're right. I mean, I should say two things. I've been using strength. I mean, you could think of strength as just purely like the quality of the roads or something. That's sort of how I want it. But I do want to think about strength as, sometimes a very reduced form representation of the strength of management or relational contracts. I am going to endogenize it, but I'm going to not allow what you said. I'm going to endogenize it, kind of requiring a firm to have the same strength with all of its suppliers. So I'm going to let you choose how much you invest in monitoring your relationships. But in the basic model, we don't let you discriminate. I actually don't know what happens if you do. It might still be an equilibrium. But I take your point that if I have a weak, but see, the thing is, the network is very symmetric. So it is not crazy to ask about a symmetric equilibrium, at least.
So in that same line of thinking, if a firm is able to deliver to half of its buyers, does that have any effect in the model if it's actually a proportional instead of a 50% we get everything out and 50% we get nothing?
That's a great question. So if you really want the purely proportional approach, you want to read the macro papers, because the way they think of disruptions is just like some kind of demon eats like 3% of your production, and you expand that to second order. Those are very interesting and rich models, and I'll try to mention some of them near the end. But for us, it's really important that there be a discreteness to the failure. Now, it could eat less than all of your production. You could fail to, but what I need like a real, you can't think of it as a little perturbation around getting everything. You should think of it as losing 30%. That would be, then qualitatively these insights would work. But if you think about it as it is, so I'm fine with it not being all or nothing, but it needs to be a sizable chunk that you lose when these links fail. That's sort of at the heart of this model. Does that answer your question?
Yes, it does. Thank you.
Sergio?
But something now, I'm reading your slide. What does mu go to infinity mean? Mu is a distribution of depths. You mean you are getting bigger and bigger depths?
It means it in probability, so that the probability, it's the limit where the probability mass on any initial segment of the integers goes to 0. So in the Poisson model, you just let the Poisson mean go to infinity, for example. That'll do it. I think, but take some distribution or the normal distribution.
Okay.
The right.
Okay. So okay. In short, some way of modeling that you are getting longer and longer depths.
Yeah,
that's what.
But I mean convergence.
But you still claim that. Okay, so let me understand. So I'm not surprised by the first statement, but the second statement says if x is bigger than some critical value, even though mu can go to infinity, even though the depths can go to infinity, you still get a positive. I guess R crit is positive. Yes.
Exactly. Yeah.
You're not saying anything. You get a lower bound, a positive lower bound on the reliability or on whatever they call it.
Because we're at these guys, right? It's kind of interesting. The redundancy, some branches are failing and you're losing them, but enough branches are kind of appearing due to redundancy that it's enough. And
that will happen at every level, you mean? Yeah. And that's why the whole network will survive. Because you'll have something like this at every level, and I see. Okay, that starts making sense. Okay, good. Thanks.
Good. Okay. So one thing, I continue to welcome questions at any interruptions at any time. So we looked at simple. Okay. So one, I want to say, from the beginning of this project too long ago, Eric asked me. Is this an artifact of symmetry? It's a natural thing to suspect. You might think that the symmetry I've set up, I told you that I studied this foolishly symmetric, n, m are constant. The depth is some distribution, which is kind of not dependent on who you are. Or you might want to put heterogeneity and all these things. I'm going to not make you suffer through the details, but I do want to tell you that there is a natural multidimensional generalization which delivers the core insight in a more more robust way. You can look at a system where there are many types of nodes. If you know how to construct something like a multi-type random graph, just do that. Specify for these types what is their n, what is their m, what is their characteristic depth distribution. Maybe they have different x's. Put all that data in, and I promise you can write a fixed point system. It'll be messier, but you can write an analogous system, which will be a system of n nonlinear equations now, which says as a function of everything that is going on with other types, what is your probability of functioning? Of course, your type specifies your linking probabilities to other types. And so you'll get an equation like this that, for a deep type, he should look sort of there's a kind of fixed point quality at infinity. And so you have this recursive thing that the deep types will have a reliability that's basically a known function of the other deep types stuff, and then some error that we can control. And you can generalize. The basic idea is that if the multidimensional generalization of this function is forced to stay low near zero, again, the equilibrium can't gracefully degrade down to zero. It has to collapse kind of catastrophically, right? So you can, once you take this multidimensional perspective, you can sort of generalize the force that was making the precipice happen to a multidimensional situation. We have that in the paper. It's messy, but the insight is actually not so difficult. And so I guess I should say that this is related, at a very high level, this is related to random graph models, epidemic models, viral spread of information. But somehow it's very different because, again, those models typically have this shape, and our model, because of the complexity, has this other shape. So the last thing I want to, I'm going to tell you, I have one more board's worth of material, but faster this time. And I'm going to tell you what happens when I endogenize stuff, but I can tell you mostly in pictures. So that's the last thing that I'm going to do. This is stuff you've seen. We're going to now make relationship strength an endogenous choice. So each firm chooses a relationship strength investment number, XIF, which is how much it wants to spend on forming relationships, or how strong it wants its relationships to be. It does this upfront. So this is like hiring managers at the start of the year. You hire your logistics team and you buy them software. And then the realized supply network with all its exact details will be realized after that. And the key thing is that in this network, all your links will work with probability XIF. So you've chosen the probability that you are able to successfully source. And C is a cost function. Of course, this investment isn't free. In order to achieve a certain level of reliability, you pay some kind of cost which satisfies standard conditions. It's going to be very expensive to get perfect reliability and this kind of thing.
So you're trying to essentially make a profit generating function?
Good. So yeah, exactly. So I'm specifying a cost so that I can tell you a full payoff in the investment game. Is that what you're asking?
Yeah, I see. I just seeing what you're doing.
I've sort of started telling you an investment game, and there's only sort of the second part of the investment game is that we realize the network, we decide who can function, which was what the last slide was all about, and then the firms that are functional. Of course, you don't sell anything if you're not functional this month, but if you are functional, you sell and you get a gross profit, and because it's close to the end of the day, where I'm not going to bother you with certainly foundations for this. But again, if you write down a totally standard model of monopolistic competition in this world, you're going to get that people make the amount of gross sales you make is decreasing in the reliability of the rest of the network. Basically, it's good, it's intuitive, it's good to be around when not many other people are, because you get to serve a larger share of the demand. So there's this gross profits function, gross because it doesn't include your costs of investment, this gross profits function, which is decreasing in kind of the economy's reliability. And then there's a shifter, I'm just putting a kappa up here, which is a multiplier that scales up the profits to the firms of producing. It's going to allow us to mess with their incentives and talk about economies that give them better incentives to invest. Like when the product is more valuable, they're naturally going to be more interested in investing to make their production robust. And so we're almost here to showing you the economic results. What I'm going to be studying is what I call a symmetric undominated equilibrium, which is just an equilibrium. It's all firms are good. So we're going to have some supply network with deep depths, let's say, and each firm is going to look at the reliability that's around it and best respond, I guess it's time to start talking about the fact that when you decide how much you should invest, of course you care about how reliable are your counterparties, because that's, you know, what you want to do is produce, and it matters how reliable they are to how strong you want to make those pipes. And then we'll make a selection. When it matters, we'll pick the most reliable equilibrium, which is kind of a Pareto dominant selection. So here, let's look at, so you already know this picture. I'm just going to show you the rest of the paper in one more curve on this picture. This red curve gives best response investment behavior. So the idea is that for any R, you can imagine that there's a reliability here that prevails in the economy. And you ask some random firm, like, this is the reliability of a typical one of your suppliers. How much do you want to invest? And you'll get an X number out, right? I mean, it might be a correspondence. Let's say it's nice. If other people are very unreliable, the answer will probably be 0, right? If my friends aren't really good at producing, then I basically am happy to not invest anything, because I'm probably not going to get any production, so it'll be 0 here. If they're very reliable, I actually don't want to invest that much either, because, and this is related to what Nikita and I discussed, because they're very reliable, so you don't need that many working pipes, you don't need that much redundancy. And so there's some kind of shape that this thing has. Crucially, as we vary kappa, as we vary this multiplier and make production sort of more profitable, we're going to move around the best response curve. And of course, as you lower kappa, you're going to move it in the worst direction. You're going to get less investment when the technology is less productive. People are going to be interested in investing less in any kind of situation. And that's going to give you this kind of movement. And here's what I want to point out. If you look at the top, of course, the intersection is an equilibrium, right? An intersection here is a point where everybody wants to invest this much in response to this reliability level, and that level of investment by everyone gives this reliability level. So that's kind of an equilibrium condition. As we move this curve, at some point the equilibrium starts lying on the vertical part, on the cliff face, on the precipice of this green mechanical curve. And for all the kappas between this one and this one, right? So here's a value of kappa, and here's another value of kappa. For all the values of kappa between these two, the intersection will be somewhere right on the vertical piece. And so that means that there's going to be an interval of kappas with the property that, when you're in this, and we can prove that it's positive measure. There'll be a positive measure interval of kappas with the property that endogenously the economy is right on this precipice, right? So you might have thought, before I showed you this, you might have said, look, okay, it's cool that your economy has this precipice, but I don't really care because I spend all my time over here, right? We're all robust and we don't ever go near this dangerous part. But no, I'm telling you that there's an open set of parameters in this economy, the productivity parameters kappa, which are going to put us directly on the precipice in equilibrium. So there's sort of 3 ranges. When kappa is really good, you can produce and you're not on the precipice. Here you're in the critical range. And then for low enough kappa, can't produce at all.
So for the highest K of the 3, if we could look at that picture, is it reasonable to think that we would somehow be able to stay on that precipice on the lower level of the best response? Is that reasonable, or are we automatically going to go all the way to 0?
You're saying if we drop down from here, can we somehow get caught here?
Yes.
Yeah.
Is that reasonable?
So here's what this is good. So I'm actually going to give you, I'm going to formulate fragility. Why do I care about these critical outcomes? Because they're fragile, and I claim that you drop and you suffer severely. Now I need to specify what I even mean by this kind of shock. What is my model of COVID in this model ultimately? I'm going to model it very naively. I'm going to say that we're going to have a small shock to X so that everybody was intending to play XIF, but unfortunately, our relationships now work a little less well than we counted on normally, right? So we just get an epsilon hit where basically we get exogenously moved to a different point on the x-axis without getting a chance to best readjust all our investments, right? So we get knocked down here, and then we're going to be, what this result says is, of course, all these critical equilibria are under this definition going to be fragile. Little shocks are going to result in not being able to produce anything. So your question would be, I mean, my notion of shock doesn't let you stay anywhere at these x's. It forces you to go down a little bit, and then there's no equilibrium at all, right? For x's lower than that. We could ask about the adjustment questions, but that's not here. You might complain about the shock that I described being unanticipated, and all of this is completely robust to anticipated shocks, because you see that what causes the precipice problem is really something, quite robust here. If I put in a small probability anticipated shock, it's going to change the best response curve a little bit, but it's not going to kill this phenomenon. Coming back to the New York Times, even if these firms are somehow altruistic or motivated to care about the macroprudential situation to some extent, you can still have, for some amount of that caring, you can still have this situation, remain robust. So it's certainly not, I mean, one punchline of this is that being in a fragile state is certainly not misoptimization. And there's nothing much that a firm can do about this, right? They're just at X crit, that's the optimal amount to invest. If the firm invested more, the whole network would still be susceptible to this collapse. So it's not like the firms individually can get themselves out of this bind. Questions, thoughts?
Yeah. Before, I thought you were going somewhere else, but let me check my intuition. Before going to the multiple, just take one firm. Okay, suppose it has and let me make it even simpler rather than a cost function. It has a limited budget of the sum of the x's that it can invest along anything it wants in its network. Okay. Now my intuition would be that among the n, it's going to select always one and put everything whatever on one, and among the m is going to equalize. I think that the convexity concavity there should give something like that. That's probably going to be the best. So rather than putting x1 and x2 on two substitutes, I'll put x1 plus x2 on one of them. That improves my chance. And rather than having x1 and x2 on two complements, I'll put x1 plus x2 over 2 on each one of them. Somehow that seems to me like the optimum. So, and in principle, you could solve such a problem from a point of view of just a single firm that is caring about its whole network, its whole supply chain. Okay, before going to the competition between them, which is what your model here has.
So just to be clear, are you imagining the firm actually also is it deciding investments way upstream of it, like 2 or 3 steps?
Yeah, on the whole, that's why I said the whole network. It looks at the whole network. It has a certain budget to strengthen links or to make the links or to essentially, let's say, there's a certain budget which is the sum of XIF over everything in that whole graph that you told me, okay, that you drew, okay. And this will distribute that thing. Of course, you can put a general cost function, but I just took the sum because that's something I can easily think about. But you'll do it more generally, of course, and better. But as a first step, it's just one firm. How did allocate its resources in strengthening its own network to maximize the probability of getting a thing? So I think that the way the substitutes and complements work is that in one case it's going to go on one, just select one of the n, and in the and among the anytime there is an m which are complements, meets all of them, you'll equalize. Somehow that seems to me like the optimal solution. Maybe I'm wrong.
No, that's great. I haven't thought about, people ask, I mean, this is like, you're thinking of like old Honda or Toyota sort of looking 10 layers deep and deciding exactly what's going to happen.
Yeah, where to invest and how much and it's not clear to me whether the different levels also, the more interesting question, once you see at each level, I think what I said is probably correct, or some version of it. The question is, how much do I put in level 1? How much do I put in level 2?
Yeah. So that's a
Okay,
very
and there is some equalization among those, and I don't know. It's just an optimization problem. It's not an equilibrium. Just a
yeah.
plain optimization, which will be of interest to say, look, I care about I don't care about that. I care about my, and I'm going, and since my depth is known, again, at least I know my depth. It's not a random model now. Let me see what I should do.
Yeah, that's a great. I'm very interested in that. I haven't thought about this optimization problem, but I agree that it's not obvious. It's not at all obvious how you divide it.
Yeah, I thought that that's where you are going, and then suddenly you went to
I was,
equilibrium. That's a different. But
that's where
I was working in my head what will be now the solution to that, and then I realized that you are not doing that. So okay.
that's what I would do if I were smarter.
No, that's a different. It's a different question. It's a different question, but maybe it gives something interesting. Maybe it's going to be a triviality.
No. It is very. I think it is very interesting, and actually, I'll say one practical thing about that at the end. So okay. So here's a small thing coming. I think this is an issue that has sort of come up in a bunch of questions. So I want to. This is just a little schematic sketch, but we've been talking about comparative statics of various kinds, and one thing you could imagine is, kappa is maybe a property of your overall economy somehow, or you have a fixed kappa for some reason, but you consider different m's that could be the different complexities that could be paired with that kappa. And here in green, I've plotted this critical region. So for a given kappa, when we solve the model for particular parametric forms that we plug in for G and everything else, this is a phenomenon that we can prove is true, but I'm showing you an example. So for this value of kappa, if m is 2, if production is fairly simple, we're outside of the critical range and we can actually produce robustly. For intermediate levels of complexity, like 4 and 7, you can produce, you can produce, but it's fragile. And then once you get to complex enough, you can't sustain that production at all. I'm talking about it as a thing about kappa, but to my conversation with Eric earlier, the question that Eric asked me at the beginning, I could think of this kappa as a parameter in the cost function, something about distance or probability of disruption, and reinterpret this as saying, as I vary the environment, what are the prospects for equilibrium producing robustly or even at all? Any questions on this?
So after all of this, after all your work, I'm curious what you and I guess the model really have to say about this kind of backlash to globalization and to these complex supply chains. Do you feel like it might be better to pull back in that restraint? Or are we seeing that this is just how things are and we do actually appreciate benefits of globalization?
That's a great question. So that's it. I'll hold I'm going to tuck that away and start concluding and say something about that soon when I won't be rambling.
Perfect.
So one thing, and this ties into Eric's talk yesterday. Okay, so Eric talked about robustness in kind of simple examples like two substitute guys who can give me the vaccine, right? And his talk, I think, really lucidly laid out the basic mechanism design thinking and reminded us that we can get surprisingly good outcomes, through being clever about prices and rents and these kinds of things, right? So here, the model implicit this, I tried to sort of sneak this by you too fast to even talk about it, but in here, you get paid for producing the same price regardless of the strength of your links that you chose, and regardless of the network realization. When we do the micro foundations for kind of technical reasons, we make all the profits come from selling to consumers. And the consumer doesn't really care about how you made your thing or how robust you were. They just care about buying the output, right? And so all the profits come from consumers. That obviously is an inefficiency from the perspective of Eric's considerations yesterday. You would like to reward firms when they're when they're socially pivotal, when they're providing the social value of making the supply chain work. Now, so a first observation, and this is before before globalization thoughts, a sort of conventional economist thought is that price gouging can be good, and in supply chains, if you can really get the rents of being the one robust guy in a disaster, that could be good for investment incentives. But one thing I want to point out, and something that we have worked out, at least in symmetric examples, is it can be the way these networks work, it can be that there are too many firms on the precipice. There's going to be a lot of firms that are simultaneously pivotal. So you can't give the marginal product to everyone subject to budget balance, right? You need to move money. If you want to keep it, if conditional on a realization, you want to bargain over the money that the consumer is paying you and allocate it in some way that's going to give people the right rewards, that turns out to be very difficult. So there's not, I mean, one kind of interesting thing is that in one-tier networks, basically, if you let, whenever I'm a monopolist, if you let me just, charge a monopoly price and extract all the rents, that's efficient. That makes me have the right incentives to be the sole supplier of the good. But when you pile up these nested dependencies, there might not be enough money to go around to pay all these pivotal monopolists. And so it's not, all I want to claim, and I'm not showing you formal results anymore, I'm just giving you a general sense that I don't think there's some mechanism design ex post of the network realization that's going to make things work. We need to think about subsidies and investment in a more kind of ex ante sense. And to the question about globalization, I think a big debate in the national security conversation is that, of course, for kind of critical industries, you have a lot more control over that within your own borders. So to the extent that we think there are externalities that require government regulation intervention, it may be harder to do that when there's a lot of the supply network that is completely outside any kind of jurisdiction. So that's certainly if you really want to be on the safe part of the curve, that's where you should be. So a bunch of these things, there's a bunch of robustness things that I said, like you can have more heterogeneous economies. You don't need to drop all the way down to zero. People often ask me, do you really think the economy freezes and produces nothing? No, I don't think that. But once you have this model, you can add bells and whistles to make it more realistic. And of course, you could embed this.
You should apply a SEER model to that. There are susceptible firms, there are infected firms, dead firms. Maybe you can combine the two talks today.
Yeah.
And see where is the critical, where is the herd immunity? Yeah. Okay.
Yeah. Let me say since this is such a nerdy audience, I want to say a few small things. So here we had a continuum population, and so all the complexities of networks entered in the shape of the row function. I didn't have to, a lot of people are working on models where they look at discrete links. Should I have this link with Eric? Should I break the link with Elhanan now to save, and those discrete models are very combinatorial, and they're very good for they're very good for publishing papers, but they're arguably, it gets very hard to solve models of this level. It gets hard to say much about settings like the one I told you. And so I kind of do, in this paper, the Mats and I do this kind of search type stuff, very much in the spirit of what Glenn talked about, and these kinds of approaches that let us endogenize probabilities rather than links, and that gives us a lot of tractability. The other trick that was technically important is that in all the proofs, I can kind of study the infinite depth model, which has a huge amount of symmetry. It's like a fractal, right? I connect to Sergio, but his tree looks exactly like my tree. And that gives me very simple fixed point equations that I can totally solve basically on graph paper, and then do the approximation that shows that actually works for finite networks, which of course is what we have in the real world. There's a cool gadget that mathematicians are very excited about called graphons. Here's just a random paper by Salman Errol, Francesca Parisi, and Alex Teitelbaum that's circulating, where they do contagion with graphons. Graphons are like a very rich random graph primitive that lets you have lots of heterogeneity. And I want to suggest that we can take kind of graphon richness and bring it to supply networks and ask interesting mathematical questions about, percolation and stuff. I'm kind of done with, I'm done with the substance of what I wanted to say. I want to close on one thought that So there's a beautiful, the CEA, it's on the Council of Economic Advisors website. And this was written, this is a cool, they have beautiful documentation of this freeze that we're going through. Evan Soltis is an MIT grad student who's a super policy wonk, and Sue Helper, his co-author, is a more senior economist at CEA who actually spent a lot of her career working on the ethnography of supply chains. And to questions like Sergio's, right? So she claims that in this case where cars are not, missing chips, apparently trying to X-ray down into the intermediate layers or tiers is difficult because there are trust problems. Like if I let you see you might want to cut me out if I introduce you to my suppliers, right? On the one hand, you want to maybe help me invest in my relationships and keep my network robust. But on the other hand, that requires kind of this umbrella of a good relational contract where we're not worried about various kinds of, defection happening. And so Helper, at least, is worried about this. And she has a lot of papers where she sort of documented this. This isn't just an opinion on a blog. And a related point is that, as we said, stable prices can actually be a little bit, they can under-provide incentives for ex-post reliability. But on the other hand, stabilizing prices and preventing holdup is one of the big things that relational contracts do. So I think just broadly, the interaction of network formation and contracts seems really important, both within organizations and in these decentralized supply networks. I've shared the slide.
Ben, so the first bullet, or not bullet, the minus, bullet with a minus sign, yes. That suggests there may be two kinds of nodes. One node takes its suppliers and has value added, has some technology or something that has value added. Another node is someone that has just connections and he knows the right guys. Now, the second guy can be replaced and you can bypass him by going directly to the suppliers. But a node which has value added technologically, you cannot replace. So that says that there is so what they are worried is about only one kind of nodes, not the other kind.
Yeah, that's a good point. That you want that if you can really put value added as opposed to just middlemen, right? So for masks, there were a lot of middlemen who all they did was just make a bunch of phone calls and send orders, right? And they didn't really have any. So and you're saying that you would be worried that the real know-how guys wouldn't be worried about being disintermediated.
Yeah, right. I mean, if they have some patents or they have some technology or they have some real value added, I mean, they cannot be replaced. I mean, again, everybody can be replaced. Somebody, the bigger firm, the upstream firm can decide to do this in-house and so on. But it will be much more difficult than somebody who just has the connections and he makes the phone calls, as you said, or runs the internet to get things from A to B. They can be replaced. Yeah. Okay.
So I think given we've had a stimulating and full day, so I think for the students especially, I've put this list of papers. Bakai and Fari are really, this is like zooming in on one little piece of supply, but they talk about how you do the accounting when both supply and demand are affected, when they interact. They can amplify or mitigate each other. There's a bunch of beautiful papers. If you're into theory, there's a student who just graduated, a student of mine who did a technically closely related model, but simultaneously he kind of independently came up with a lot of related ideas, but for thinking about innovation and the emergence of innovation hubs. So I think it's an exciting. I mean, the supply network stuff is really thriving in kind of applied economics, and then there's also, I think, really exciting theory to do. So that's all I had, and of course, I'm happy to take any questions, but just very grateful to have had a chance to present here.
Thank you. Thank you.
Thank you, Ben. I actually, I'm a bit confused about, or not clear enough about the market failure that is happening. Let's talk maybe first about the real world.
Yeah.
And then maybe I might have missed something, probably missed something in the model you described. But if we look at the real world, okay, what is the market failure that we could point out to? There is certain shortage in supplies of certain materials, so the price is rising. It becomes more profitable to supply them. Transport, so the transport prices are rising, so there's incentives for the transport in the industry to expand. What is there a market what is the market failure, if there isn't?
I think the key thing is you just don't appropriate the way the rents are allocated. You don't appropriate your marginal contribution to social surplus in the way that I'm doing the pricing. That is, even if when I run the if every supplier kept their full marginal contribution to their basically did sort of all the bargaining power was upstream, then I think what you say would have a chance of working. But the thing is that I guess what I'm saying is, if I maintain my truck extra well and I can bring you the stuff, I do get paid the price. But unless I can, raise, if we have a usual price, and on the day when you really need my stuff, I come and I raise the price, right? That's one protocol. And then I could hope to appropriate my contribution. But if I have to sell to you at the usual price, then then you and I share the social returns of my investment in reliability, and it's not, and therefore I will not always make the full socially efficient investment at the margin. It's kind of in the bargaining protocol. There's nothing profound about the inefficiency, but I'm not letting the guy who invests in X appropriate all the rents.
Yeah. The guy who invests in the relationship, can you make that shorter? The guy who invests in what?
Yeah, in this model, invests in X, which means hiring more management, doing more spot checks, just doing the things you do to monitor your supply chain. All these people downstream of me benefit from that, from my doing that, but they don't pay me the full amount it's worth.
Mm-hmm. And now, taking this model into the real world, what is this kind? How would you describe this kind of investment exactly?
I think it's stuff. I mean, there's a huge ethnography. Matt Elliott has read more of it than I have, but like people like Uzi have just like a huge amount of like visiting factories, querying when you get instructions that seem like they have mistakes, calling the guys to check, like the kind of the supply chain, these logistics experts that kind of monitor, that try to predict failures. I think it's stuff like that.
Yeah. Of course, you have in the market, services that give you information on, in principle, and I think in practice also, you have services that give you some information about the reliability of suppliers, about their situation.
Sure. Oh, yes. So yeah, these models, that's a great, if you had this also comes up in financial networks, right? People write papers saying, oh, there's this inefficiency in financial networks. Somebody says, just make a good enough credit rating, and then everybody will be able to sell their good credit rating. But somehow these credit ratings that take into account all the systemic stuff aren't really available. And I think it's a kind of deep question why they don't, why the ratings that we have are too coarse and stuff, but.
Okay. Any other questions? Okay. Thank you very much, Ben.
Thank you so much. This was, thank you folks for staying.
Thanks. So we meet together.